This is our video on pressure. This is the first video in our section in our series on water hydraulics. And what we're going to do in this series is give you an abbreviated explanation of the factors of water hydraulics. We can't really cover all of the physics of it. Really, if you got down into all the details, this is probably a semester's worth of information. If you went to a university and took a class, I mean, it is a semester's worth. And typically they're going to call it fluid dynamics. So don't come at me with definitions or whatever, because, you know, if you look at any of the industry sources, whether it's the Irrigation Association or Rainbird or Hunter Industries or whatever, they all call it water hydraulics. So that's what I'm going to call it, right? And there's four factors to this. There's pressure, flow, velocity, and friction loss. We're going to deal with the other three in other videos, but for now we're going to talk about pressure. Now let me give you a definition of this, that hydraulics is the branch of science that deals with water either in motion or at rest. And our primary goal of knowing about water hydraulics and knowing how to calculate it is to ensure that for our sprinkler system that we're going to have adequate and continuous pressure. Our secondary goal in calculating this is to only use the minimum size of pipe and fittings that we need to in a system just for cost efficiency. Now let's talk about the definition of what pressure is. Pressure is the potential to push the water through the pipes, right? It's an energy potential, and you have two different ways of measuring it. You have static pressure and you have dynamic pressure. Static pressure is the water not moving, right? You've got water up to your irrigation system, and we can put a gauge on it and measure what it is as it's sitting there under pressure but not moving, right? And let's say that we've got a system and we've got a water gauge on it at the beginning of the system, a pressure gauge, and it says 100 psi. And we go and turn our irrigation system on, and the system is well designed or properly designed, and the water starts flowing through it. If we go back and look at our pressure gauge, it's probably going to be about 70 or 75 psi. It's usually about 25 or 30% less dynamic pressure than static pressure. And now, of course, that just is, depends on how it's designed, how many open heads that there are running on a zone, and so forth. But you get the idea. Let's say that you're standing here at a door and you've got your shoulder up against the door. The door's closed and you're pushing on it with all your might. That's static pressure. If you took a weight scale that like you'd stand on to check your weight, and you put it between your shoulder and the door, that would measure how much force that you're pushing against that door. And that would really be the equivalent of our PSI, right? But if you open the door and now we're running down the hall, but the hall is only narrow enough for us to fit through it, and our elbows and our shoulders are scrubbing against the sides, right? Because that's how it is if water's flowing through a pipe, because the water is actually contacting the pipe as it flows through it. That would be dynamic pressure, and it wouldn't be as much as our static pressure. Because if we're standing there just with our shoulder against it, we can give it all we got. But when the door opens and we start to run down the hallway, it's going to be at less force than we were when we were just standing still, forcing against it, because we have the friction of us brushing against the sides of the walls, and the air that's blowing across us is friction as well. So you're going to lose some of your energy when the water gets into motion. And now we have two different ways of measuring pressure. The first is PSI, which stands for pounds per square inch, and then you have feet of head. Let's talk about PSI. PSI, pounds per square inch, is the measurement of a single column of water, right? A straight up and down vertical column of water that rests on 1 square inch. Now, it's not cumulative. It doesn't matter if your column of water is only 1 inch, like you've got a 1-inch pipe, or it's the size of a lake. It doesn't matter. We're only measuring what lands or what's pressing down on 1 square inch of the bottom, right? And so if you've ever been diving or snorkeling or whatever, you know that as the further you go down, you can feel it pressing on you. And there's only so far down in water that a human can go before you get crushed. And I don't know if you saw a news item from a few years ago, a submersible, like a submarine, went down and it wasn't properly designed, and they got down to a certain point and it just got crushed and it killed everybody in that little submarine. It's because they crossed the threshold of the makeup of that submarine wasn't able to withstand the force. And that's not some crazy physics or anything that's hard to explain. It's just the weight of water. As the further you get down, there's more water that weighs down on you. And I think water weighs maybe, what, 7 or 8 pounds. If you had a gallon of it, if you're holding a gallon of water, that's about, I don't know, 7 pounds or something like that. So it's the weight of water that's pushing down. And so for every foot of water that's pushing down, it's going to be 0.433 psi. And psi is what's used here in the United States and in other parts of the world. They use a metric system. And in the next video on flow, I'm going to give you a longer explanation as to why I really can't teach side by side on both imperial and metric at the same time. But where I can, I'm going to give you a conversion factor. And in places we're talking about specific numbers, I'll try to give you the conversion over here on the right side of the screen. But the conversion factor is this: 1 psi, 1 pound per square inch, equals 0.0689477 bar. And 1 bar equals 14.5037738 psi. Now, when you're calculating this out, you don't have to go 7 digits beyond the decimal point. I generally calculate it at 3 places. And a lot of times that's not even really necessary if you're trying to just come to your basic calculations for designing an irrigation system. But this conversion factor is going to be in the PDF download. So if you hadn't already done so, go to the very first video in the course and download that, and also download Hunter's friction loss charts. We're going to be getting into that a whole lot more. So let's talk about our other measurement, and that's feet of head. You're not going to see this a lot until you start getting into pumps and calculating what size of pump you need for the system and so forth. So a feet of head is the measurement of 1 foot column of water, right? Which is 0.433 psi. So 1 foot of head equals 0.433 psi. 1 psi equals 2.3 feet of head. Now, that's not going to mean a whole lot to you now until you get into pumps and so forth, and really PSI is the only thing that we're going to be dealing with. Now, when we're talking about an irrigation system, there's only 2 main ways, or really 2 ways at all, that we're going to be able to make pressure or increase pressure in the system. One is from elevation, right? And we're just talking about that. The weight of water pushes down and increases the PSI by 0.433 PSI for every foot that water drops downhill. Now, conversely, if you're trying to push water uphill, for every foot of water you're pushing it up, it loses 0.433 PSI. So that only matters in a completely vertical column. If we're trying to measure what our pressure would be, let's say the source is at the top of a hill, your house is at the top of a hill and that's where it connects to your main water line, but you have an outlet, a head or a zone down at the bottom of a hill, and we're going to try to measure that. And let's say that the source is up here and way down here is the outlet that you're going to try to measure. Well, it doesn't matter the length of that pipe or the angle it goes down. The only thing that matters is on the bottom and at the top. And I've got another video that's going to show you how to calculate that. But really all we're trying to do is find out what the difference is between the top and the bottom. Like I said, it doesn't matter if it's 20 feet away or 5,000 feet away, or how long that pipe is or whatever. And so how you would measure that is really, you would get a piece of pipe and stand at the bottom, and you'd have another person at the top of a hill with a laser that's setting a level that's hitting your pipe, and then you would measure how many feet up that laser hit your pipe, right? So it doesn't matter how far away it is, the angle, the size, the length of that pipe. The only thing that matters is a straight up and down. So that's elevation. The other way is with an electromechanical pump. Okay. So when you're looking at the city water system, those are the two ways that they're going to give you pressure, to your house. One is they're going to use a water tower, right? Now we see a water tower here that's local to me. And really what they're doing is they're just storing water in a tank at elevation that's pushing down on the water system. Okay, so that's one way, but somewhere also on that water system at Greenville City Water, there's going to be pumps that increase it. And those are really the only two ways that you can do this. Now, there's two other ways that pressure happens. The other is heat, right? As water gets hotter, it expands. And so in like tall buildings in New York or wherever, some of these buildings use a boiler, down in the basement to increase heat. The boiler heats the water up, which pushes it and increases the pressure in the line. The only time that you're really going to deal with heat and increased pressure in an irrigation system is if you have a pump. Like say you've got a lake pump and it's running badly, the bearings are going out or something, and it's heating up, then it will increase the pressure in the line. Usually it'll blow a pipe out and it'll blow a big knot in the side of it or whatever, but that's because the heat is increasing the pressure of the water in the line. Now, it doesn't really work in reverse. I mean, a little bit, cooler water can compress the water a little bit, but water can't really be compressed, not in the way that air can, right? We use air compressors and we can push air and compress it into a tank and then use that to fill up tires or blow stuff off or whatever. But you can't really do that with water. Technically, if we look at the physics of it, yes, water can be compressed, but it takes so much energy and so much pressure, really an immense amount of energy to compress water, and you can only compress it just a little bit. So that's completely impractical for us to do in any way. So heat, compression of water, that's not things that we really deal with for the most part in irrigation systems. But there is another way, another type of pump that's not electromechanical, it's just mechanical, and those are hydraulic ram pumps. Now, there's some tricky things to that, and there's only so much you can increase the pressure using affordable parts, right? If you're using 1-inch parts or whatever and trying to increase pressure into the system, you can push water uphill. And I think the calculation is something like if you had the problem is that you have to have some pressure pushing down on this ram pump to be able to push water back up. It can multiply that. But let's say that you had water that flowed downhill 6 feet. You could push that same water up 30 feet, but it would only be at 14 psi. Now you can get larger parts, and what this does is it uses 2 swing check valves and a column between them, and it kind of pops back and forth and pushes that water up. And you can build ram pumps that can push 100 psi, but it is completely impractical for irrigation systems. And if you're watching this video and you know of a residential or light commercial irrigation system that uses a hydraulic pump, a hydraulic ram pump, get in touch with me. I need to see that. I need to know the calculations and the cost and all of that stuff. But for the most part, if you're working on residential and light commercial irrigation systems, just go ahead and put that out of your mind. Maybe if you're in the third world and you need to get water from a stream and push it uphill into a tank and then use that tank to flow back downhill and push, a small drip system or something, that's definitely possible. And there's videos out there to show you how to do it. But for irrigation systems, that is entirely impractical. Now, among the other factors of water hydraulics, I mentioned before that there's pressure, flow, velocity, and friction loss. Now, unfortunately, if you don't understand water hydraulics, a lot of people are going to blame everything on pressure. You walk up to a system and the water's barely pressing out of the heads and not really performing. Most of your beginners or whatever are going to say, hey, it don't have enough pressure. Well, what you don't know is that they didn't design the system right. And when the system should only have had 6 heads, now they've put 20 heads on it. Maybe another contractor came in and just started adding heads. It happens a lot in garden systems. And I've come across this myself out in the field, where you have a zone of sprays out in the back, and you have some new garden areas, some new little raised beds or whatever, and they've put a bunch of new heads and stuff on there, and now it doesn't work so good. And they say, well, we've run out of pressure. We don't have enough pressure. Well, technically that's true, but what happened is you over demanded flow. And all of these things work hand in hand. They don't exist. Pressure, flow, velocity, and friction loss don't exist in vacuums from each other. If you increase pressure, you're going to increase the flow, right? The pressure, a higher pressure is going to push the water, more water through the pipes. But here's the trick with it, that your velocity is going to go up, and velocity is the speed with which that water is moving through the pipe. We'll talk about that in a later video. But the faster that water goes through the pipe, the more friction it encounters on the inside of pipe. It's going to cause friction on the inside as it's moving, and the faster it goes, the more friction. So there's only a limit to where you can increase your flow by increasing pressure. Now, as we go through the rest of these videos, I'm going to get a little bit more into this so you'll understand. And it's kind of a relationship that higher pressure equals higher flow, equals faster velocity, equals higher friction loss.